what we'll be working with the next week or so is sound. And we're going to have some special types of waves that we'll be playing with, okay? And just so you can remember a couple things, we had two different types of waves. We had electromagnetic, right? Remember everything coming off the EM spectrum? You had visible light. You know, when you got smaller, you got ultraviolet, right? You got X-rays, you got gamma rays, you know, you got infrared. You remember the deal. Mechanical waves, remember, what is it the mechanical waves need? They need a medium, okay? The other telling sign on a couple things is figuring out what's out there is, you know, looking at something by its interference pattern. Remember, you had constructive, you had destructive, okay? Sound waves travel in compression waves, okay? Sound waves travel in compression waves. When you speak, your voice compresses air. You know, tuning forks compress air at a regular pace, okay? So what it's, these are longitudinal. So think of these as our slinky. When they're real tight together, it's a compression. They spread out, you get a rarefaction, and then they tighten up again for a compression. Is there sound in space? Probably not. In space, no one can hear you scream. Okay? Factors affecting the speed of sound, what we'll look at, the general overall number is this 340 meters per second. Other things that come into play, sound works better in hot air due to the increased speed of the molecules, and it also moves fastest in a solid, then a liquid, and then finally in air, okay? The molecules are closer together in a solid. That's all there is to it, okay? I don't have any of these sounds worked into the show. Sound is measured with a decibel. It measures sound intensity or loudness. Loudness, that loudness is the amplitude of the wave. Okay? The unit is a D, little d, big B. Okay? Of those sounds, if it's greater than 120 decibels, it causes pain in the ears. Between 0 and 120 is what's audible. Below 0 is subaudible. Okay? The older you get, these numbers kind of, the 120 goes down and the 0 goes up. Okay? Pitch. When we get into music, and we're going to try to bring in some musical instruments, but the pitch is the frequency. High pitch, high frequency. Low pitch, low frequency. If you want to know what we can hear as far as what the frequencies are, being 20 and 20,000 hertz. Above 20 is ultrasonic, below 20 is subsonic. Okay? It's how much you can hear. We've all had those little hearing tests before to see how big of a range we actually have. This Doppler effect is kind of cool. I tried to pull up this website, and it's not going. If you want to see a goofy video, and maybe I'll have to show these in class, is go to Google the Big Bang Theory Doppler effect. And Sheldon is actually dressed up as the Doppler effect for his Halloween costume. Okay? We may watch that in class, but if you do that, it will give you this idea. It's the change in the pitch or the change in the frequency because either the source is moving or the observer is moving. Okay? But it's that change in frequency because something is moving. Resonance. Resonance is that vibration of an object in natural frequency. Okay? Everything has its own resonance. Okay? You've all, what's that, Miss Congeniality when Sandra Bullock is playing those wine glasses. Okay? You get resonance in theaters because, somebody playing a bass, makes the drum go or makes a piano go. Or in this instance, a car alarm goes off when you drive by with your music too loud. And again, here are some other websites that have that. And resonance is just a natural frequency. It's a vibration. It's usually a forced vibration as well. Echo. We've all wanted to hear echoes. If you go to the Grand Canyon, right? If you go to the Grand Canyon and you get lost, right, and you yell for help, okay, that sound's got to go off the wall and then back. Okay? Echoes are just simply bouncing of sound. A standing wave happens when there's a lot of different waves going on and one is produced. We're going to spend a little more time with this in class, but a standing wave looks like it's doing exactly that. When it comes to a musical tone, right? If you get the right wavelength in the right length tube, okay, you get a standing wave. We'll probably spend a little more time on this. There's harmonics, right? It's a sound wave with a pitch that is a multiple of that natural frequency. Okay, if you've been in band or you've had music for a while, okay, everything has a natural frequency. Harmonics, you might be up an octave or down an octave or something of that nature. Okay? And basically you're looking at multiples of these right here. Okay? And there's a little bit of math here. Excuse me. When it comes down to figuring out some of the math. But nodes, you have nodes and antinodes. If you have a wave that's like this, okay, you get nodes, okay, and it actually looks like the displacement is 0, where two waves meet up and the displacement is 0. Antinode is the of largest amplitude, where they're constructive. So you would get antinodes, right? I think I do that right. Where the displacement is at a maximum. Again, this is, a tube with the sound wave going down this way. A couple other things that are going on. Yes. Can you give me 5 minutes? Thank you. Two other things that are going on is this idea. In music, you hear this consonance and dissonance. Okay? Consonance, you get a multiple wave combining for a pleasant sound. Dissonance, you get a wave where it actually doesn't sound very good. It sounds unresolved. It sounds like there should be another note coming after it. Some sonic booms. Well, my picture didn't come through, so I don't know what happened on that one. Sonic boom. Too bad I can't get that. You know, if you have a plane going off, remember, well, I don't know what happened here. There's my sound, okay? There's my plane. What's happening here is this fighter plane is piercing through the sound, okay? And when you're going slow, there's kind of a wall here. The faster you go, the thinner that envelope gets. What happens with this picture when you hit that sonic boom and basically you've busted through that, there's this pressure that goes behind you. That pressure pushes all the moisture out of the air. So you actually get a cloud forming at the back end of the plane, which is actually kind of cool. Here's the math. Same thing. Velocity is wavelength times frequency. You know, and harmonics, shortcuts, you know, basically you're looking at V is our velocity over here, and this one didn't come out real well, I think, when I transposed that over. Fn is the fundamental frequency in hertz, which is basically a harmonic number times the velocity divided by 2L. Okay, there's a way to shortcut some of these things as well, where this harmonic number, the fundamental frequency, is the harmonic number times whatever that first frequency is. We'll do these a little bit more in class, though. That's it. Sorry for the interruption. Hope these come through.